Hello everyone, here is Karam. In this video, we are gonna learn how to simulate fluid flow through a mixing T. Mixing T is commonly used for static mixing of two fluid streams. In this problem, a mixing T is used to mix two low-speed air streams, one at 10 Celsius and the other at 20 Celsius. The goal of this simulation is to evaluate how effectively the two streams are mixed by examining temperature profile on the cross-section of the T exit. Now let us go to Ansys Workbench and drag Ansys Fluent Fluid Flow. Now right-click on Geometry and then select Import Geometry. Now right-click on Geometry and select Edit Geometry in Space Claim. Now make yourself familiar with the Orient group in the Design tab. Test all the different view options and controls, spin, pan, home, etc. You can select the geometry and make it, for example, transparent, etc. Now let us go to File and then Close. Exit Space Claim. Now double-click on Mesh tab. It is good practice to first check and, if required, set the units. Now make sure this is selected. Metric, meter, kilogram, Newton, second, volt, ampere. Now click on Mesh. Make sure the physics reference is CFD and solver preference Fluent. Now expand Sizing tab and make sure Capture Curvature is yes. And then click Update Mesh. As you can see, a basic mesh can quickly be generated with the minimum of input. Now we need to make named selections for the boundary conditions. Select this icon to change to phase selection and then select this phase and right click and create named selection. Rename it to inlet Z and click OK. And then this will be inlet Y. And this will be the outlet. And click OK. These named selections will be used to define boundary conditions in the fluid solver, which is Fluent. After that, the fluid simulation will concern a wall-bounded turbulent flow. To adequately resolve flow gradients near the wall, we need smaller mesh cells near the wall. An efficient way to achieve this is by inflating the wall surface mesh to produce layers of thin prismatic cells called inflation layers. In the outline, click on Mesh to display the details of mesh panel and expand inflation section and set use automatic inflation to program controlled and then click update. The mesh will be regenerated with the new settings now. Review the inflated mesh. As you can see, these are the inflation layers. As you can see, the program controlled inflation has automatically excluded the named selection faces to create layers on the unnamed wall faces. In the end, the same basic steps followed here are used to mesh most models. Set physics preference to CFD, provide basic inputs and generate mesh, add named selections and then generate mesh with inflation layers. Now, the mesh task is completed. Now close meshing and return to Workbench. Now double-click on the Setup tab to start Fluent and then select Double Precision and make sure to select for solver processes and click Start. Now let us talk a little bit about Fluent GUI. This is called the ribbon and this is the outline tree. This is the task page. Here we have the graphics toolbar, and here is the graphics window, and here is the console. Now, this ribbon is used to guide the basic Fluent workflow. The four primary tabs used in every simulation are setting up domain, and then setting up physics, and then solution, and the last one, results. These are the four primary tabs which you will use in every simulation. For this case, and probably most other cases too, you will use them going in order from the left to the right. Now, in the setting up domain, click check perform mesh check. Now, as you can see, the minimum volume is a positive value, which means that each cell is in a correct format and connected to other cells. You only have to look for error messages in the output. If done appears, as it does here, without any errors or warnings, the mesh check was successful. Besides, the minimum volume is not negative, okay? Also, mesh quality. In the settings up domain tab, go and click evaluate mesh quality. Mesh quality is very important for getting a converged accurate solution. The worst cells will have an orthogonal equality closer to 0, with the best cells closer to 1. Ideally, the minimum orthogonal equality for all types of cells should be more than 0.1, with an average value that is significantly larger 0.2. But sometimes it is possible for the minimum to be as low as 0.01. The maximum aspect ratio is 17.3, which is high, but acceptable in inflation layers. If the mesh quality is unacceptable, it is best to remesh before proceeding. Now, in solver settings, make sure the type is pressure based and the velocity formulation is absolute and the time is steady. After that, go to physics and select energy. This tells the solver to solve for the temperature as the hot and cold streams mix. Now go and create edit material. This will open the materials panel. The default material is air, so no changes are needed. Now these properties correspond to atmospheric pressure and 15 Celsius. Now close the panel. In Fluent, the cells in the mesh are grouped into one or more cell zones. Each cell zone is bounded by one or more boundary zones. You will define boundary conditions for boundaries and cell zone conditions for cell zones. Now double-click on the cell zone condition. You will see that the default cell zone settings is applied for this case, which is air, and click Apply, Close. Now go to the boundary conditions, select sort or group by zone type. Now double click on inlet Y and make sure it is velocity inlet and click edit. Enter a value 0.24 meter per second for the velocity. Click on thermal and type 10 Celsius. Now we need to change the unit. Click apply, close, go to units. From domain tab units, go to temperature and select Celsius and click close. Now double click, go to thermal and select 10 Celsius and click apply, close. Now double click on inlet Z and type the velocity 0.04 meter per second, and for the thermal 20 Celsius, and click apply and then close. Now regarding the outlet, the default setting for outlets is gauge pressure equal to 0. So this is the desired value for this case. Now click apply and close the panel. Now regarding the wall boundary condition, the default momentum boundary condition for walls in Fluent is the no-slip condition. The default thermal boundary condition is adiabatic, which means heat flux equal to 0. In this problem, We are assuming the wall is adiabatic, so it is not necessary to change anything here. So click close. Regarding the internal zone, it is never necessary to open the boundary condition panel for these zones. So these zones require no inputs. Now from solution tab, select definition and create a new and then surface report and select uniformity index area weighted. For the name, type outlet monitor, and for the variable, select temperature, static temperature, and the surface will be the outlet. As we are interested in mixing and temperature distribution at the outlet, it makes sense to monitor temperature uniformity at the outlet. Now make sure you tick report file and report plot and print to console. Then click OK. After that, go to initialize and select the hybrid initialization and click initialize. After that, press run calculation and type the number of iterations 200 and click calculate. Now, as you can see, the solution is converged at 51 iterations. Now, from Results tab, select Fluxes and click on Mass Flow Rate and select the three boundaries, Inlet Y, Inlet Z, and Outlet, and click Compute. You will see here the conservation of mass is achieved here as the mass flow rate at the inlet equal the mass flow rate at the outlet. Click close, then you can go select contour and select the temperature, static temperature for these surfaces and click display. Go to the color map option, select general, apply, close and save display. And you can see here the temperature at the inlet and the temperature at the outlet. To get the temperature at the outlet as a numerical value, go to surface integral and select mass weighted average and select the field variable temperature, static temperature at the outlet and click compute, and you will see it as 10.67 Celsius. Now from this result and also from the contour, we can conclude that the temperature distribution on the outlet shows the streams are not completely mixed at the outlet position. Now, to save the results file with the case file, click on this icon tab, Update Mesh Setup Solution, and then continue. And select OK. And then click Close, and after that, go to File and select Close Fluent. And for here we have finished for today. Thanks for watching. See you soon in another video. Goodbye.